Hello there, and welcome to the Sleepy Space Channel. Tonight, we'll be wandering gently through the entire ladder of size the universe contains, from its softest, smallest end to its largest, soft edge, and discovering, very quietly, that you sit somewhere near the middle of it. We will begin with the hand and step downward, very briefly, into the atom and the nucleus and the soft, slow horizon below them. Then we will turn around and step outward, through the Earth and the planets, through the Sun and the Oort Cloud, through the nearby stars and the slowly turning Milky Way, through the family of nearby galaxies, the cosmic web, and the soft edge of the observable universe. And we will return home through the very small. The ladder begins inside you, and ends inside you, and reaches outward in both directions. If these gentle journeys help you rest, I invite you to like, subscribe, or share a thought below. It helps others find their way here too. One sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your shoulders soften. Allow your eyes to grow heavy. Let the day fade away. Let's begin. Tonight begins where you already are. Before we step outward into the long quiet of the universe, it helps to begin from the place your body already understands. So let us begin with the hand. Your hand, resting somewhere near you now, is roughly 20 centimeters across, from the tip of the thumb to the tip of the little finger when it is spread softly open. That distance, about 1/5 of a meter, is the first quiet ruler of this video. Almost everything we touch tonight will be described in some gentle relationship to it as a multiple of it, or as a small fraction of it, or as a soft comparison drawn against the slow widening of the room. The hand is a useful place to begin, because the hand is the place where intuition still works. You can imagine a hand. You can imagine two hands placed side by side, or a row of hands stretched across a long table, or a hand reaching up to touch the soft edge of a window. The body knows what a hand is. The body knows what a hand can hold. As the rooms of this video widen outward, we will keep returning to the hand, very gently, so that the size of things never grows too large to feel. So begin with the hand. And from the hand, step downward, just a little, into the smaller spaces the eye can almost see, but rarely notices. A grain of fine sand, settled on the back of the hand or on the page of a book, is a much smaller object, about 1/10 of a millimeter across. That means that, lined up gently, end to end, 2,000 grains of fine sand could lie across the width of a single hand. 2,000 small grains settled into a soft ribbon, no longer than a hand. There is a quiet stillness in that thought already. Smaller than a grain of sand, but not by very much, is a single hair from a human head, somewhere near 80 micrometers across. A grain of sand could lie beside a hair, and the two would be nearly the same width. We do not usually notice this. Hair feels like a thin thing, sand feels like a small thing, but at the soft scale of the body, they belong to the same gentle family. Both are near the edge of what the unaided eye can resolve as a distinct object. Both belong to the first soft step below the hand. Step downward again, into the body itself. A red blood cell, one of the small discs that drift through your veins as you settle into this video, is about 10 times smaller than a single hair. 8 micrometers across, give or take. A small disc too tiny to see directly, but real enough that there are about 25 trillion of them in the average body, drifting steadily through the slow, patient work of carrying breath from the lungs out to the fingertips and back again. As you breathe, the small red discs move with you. They are part of the smallest end of the ladder that, much later in this video, will run all the way out to galaxies and beyond. A red blood cell is near the soft limit of what light microscopes can show clearly. Below it, the world becomes a place where the slow craft of seeing must use new tools. A single bacterium, the kind of small living thing that has been on this planet for billions of years longer than anything with eyes, is about 1 micrometer across. 1/1000th of a millimeter. Picture a hair, and then picture 80 bacteria laid quietly side by side along its width. That is the next rung downward. 1 micrometer. Below the bacterium, the ladder of size becomes a place where light itself begins to soften. A virus, smaller than even a small bacterium, is about 100 nanometers, 1/10th of a micrometer. The wavelengths of visible light themselves are not very much smaller than a virus. To see a virus, you need not just better lenses but a different kind of light, electron microscopes, in which beams of small charged particles pass through the tiny object and write its shape onto a detector. Light, the patient companion of so much of what comes later into night, has its limits, even at this gentle end of the ladder. Below the virus, the ladder still keeps going. A single strand of DNA, the soft, long molecule curled inside almost every cell of your body, is about 2 nanometers wide. 2 billionths of a meter. That strand carries the slow instructions for everything your body builds and rebuilds while you sleep tonight. It is too small for any beam of visible light to resolve. It is, in some sense, smaller than light itself. Step downward once more. An atom, one of the tiny units that the strand of DNA, your blood, your hair, your hand, and indeed every solid thing in this room is built from, is about 1/10th of a nanometer across. About 100 million times smaller than a hand. If a hand were stretched out to span a continent, an atom would still be no larger than a small pebble lying on the side of a road. The hand is large, on the ladder of atoms. The hand is gentle, on the ladder of stars. The ladder is long in both directions. An atom is itself almost entirely empty space, very softly arranged. At the very center of an atom is a nucleus, made of protons and, often, neutrons. The nucleus is 100,000 times smaller than the whole atom that surrounds it. If an atom were the size of a stadium, the nucleus would be no larger than a fly drifting somewhere near the middle of the field. The rest is space, held together by gentle electrical forces, with electrons forming soft clouds at distances that, on this scale, feel almost impossibly far from the center. The atom you imagine as a tiny, dense ball is, in truth, a tiny, patient, mostly empty arrangement. The proton at the center of a hydrogen atom is itself only about a femtometer across a millionth of a nanometer, a trillionth of a millimeter. The proton is, by any measure, an unimaginably small thing. And yet, in the long ladder of the universe, the proton is not the bottom. Below it, the ladder continues. Inside the proton are still smaller patient bundles called quarks, held together by forces no one has ever seen with a naked eye. The quarks themselves may be true point-like objects, with no size at all that any experiment has ever measured, or they may simply be too small for any current instrument to find their edges. The honest answer at this rung is gentle. We do not yet know. Far below the proton, and far below the quark, lies a horizon at the bottom of the ladder. It is called the Planck length. It is the size at which the language of size itself begins to dissolve the place where gravity, the soft, slow force that bends light and holds galaxies together, becomes large enough at small scales to enter into a strange, quiet partnership with quantum mechanics. The Planck length is about 20 orders of magnitude smaller than a proton. 20 zeros between the proton, that already vanishing thing, and the Planck length below it. No experiment has ever measured anything that small. The Planck length is, in the quiet way that horizons are, a soft floor, a place where our seeing softens and gives way to something we do not yet know how to describe. But you do not have to picture the Planck length tonight. You only have to hold this thought gently as we begin the long walk outward. The Planck length is the bottom of the ladder, somewhere far beneath you. The universe goes downward into smallness for at least as many steps as it goes upward into largeness. And humans, those slow, patient creatures who can imagine such a ladder at all, sit somewhere near the middle of it. A hand, 20 centimeters wide, is a bookmark placed roughly halfway through the book of size. It is good to begin here, in the smallest soft end, before we step outward. Because every great thing we touch tonight, every planet, every star, every galaxy, every web of galaxies, every quiet edge of the visible universe is made at the deepest level of these small, patient things. The hydrogen in the water you drank today, the iron in your blood, the carbon in the breath you are slowly exhaling, the calcium in your bones, all of it is built of atoms, and the atoms are built of nuclei, and the nuclei are built of protons and neutrons, and the protons and neutrons are built of quarks. The universe is mostly small. The largeness comes from how patiently the smallness is arranged. So picture, very softly, the hand. Picture, in the hand, the slow drift of blood through veins. Picture, in the blood, the small disks of red cells. Picture, in each cell, the long, quiet curl of DNA. Picture, in the DNA, the rows of atoms. Picture, in each atom, the small, dense nucleus, the soft cloud of electrons, the mostly empty space between. And beneath even that, the soft, slow horizon of the Planck length, far, far below, calmly waiting. This is the first family of tonight. The end of the ladder that begins inside you. The smallness that the body already carries with it, even into sleep. From here, we begin to widen. From here, the rooms grow softly larger. But the hand will be with us at every rung. The hand is the bookmark. The hand is the floor. Tonight is a long, slow walk from the hand outward into the largest, seeing the universe allows, and then back again into the hand at the end. Let your shoulders settle. Let your breathing slow. Let the smallness inside you become the floor that all of tonight's largeness rests upon. And beyond that, the ladder continues. Even quieter still. Even softer still. From the smallness of an atom, the ladder begins to widen. The next room is the room you live in, every day, without ever quite noticing how large it is. The next room is the planet. Step gently outward from the hand. A single step, taken slowly, is about 3/4 of a meter, about 4 times the width of a hand. A walking pace is a useful unit at the beginning of this new room. From the hand, take a step. Then another. The world widens softly. A grown human, standing tall, is between 1.5 and 2 meters from the floor to the top of the head. About 8 or 9 hands stacked end to end. The body is the second ruler, after the hand. It is the height of doorways, the depth of staircases, the soft size of the spaces we have built for ourselves to move through. Step outward again. A tree, the kind that you might see at the edge of a quiet park or along the road of a small town, can be about 30 meters tall. about 15 people stacked one on another's shoulders. 200 hands stretched end to end. A tall tree is the height of a 10-story building. A tall tree is small in the room of the planet, but it is already enormous compared to the body. The room widens softly, even at this gentle pace. Step outward again. A mountain, taller than any tree, taller than any building, taller than the highest reach of birds in flight, becomes the next rung. The tallest mountain on Earth is Mount Everest, rising almost 9 kilometers above sea level. 9,000 meters. 9,000 standing humans stacked one upon another. A long, quiet flight of 9 kilometers, if you could somehow stand at the bottom of it and look up. The very top is so high that the air has thinned to about a third of what it is at sea level, that the temperature has dropped far below freezing, that the wind moves with the slow, patient force of weather that has no respect for anything in its path. And yet, on the scale of the planet, Mount Everest is small. The deepest part of the ocean, an enormous narrow trench in the floor of the Pacific, reaches 11 kilometers down. Slightly deeper than Everest is tall. So if you imagined the highest mountain placed inside the deepest trench, the top of the mountain would still be a kilometer beneath the surface of the sea. The relief of the Earth from the highest peaks to the deepest oceans is roughly 20 kilometers end to end. About 20,000 standing humans. This is a meaningful number in its own quiet way. The Earth itself is far, far thicker than that. The Earth is, from one side to the other, about 12,700 kilometers across. 12,700,000 meters. About 630 Everests stacked from the center of the Earth to its surface. The deepest hole that humans have ever drilled into the Earth reached only about 12 kilometers down. That is a scratch on the surface of a world more than 6,000 kilometers thick. If the Earth were the size of an apple, the deepest hole humans have ever drilled would not have broken the skin. And the atmosphere, the soft layer of air through which you are breathing now, through which sunlight passes, through which weather drifts, through which birds and clouds and aeroplanes move, is also a very thin layer compared to the world it surrounds. If you measure from the ground up to the soft edge of space, where the air finally fades into the near vacuum of orbit, the distance is roughly 100 kilometers. About 11 Everests stacked end to end. But most of the air is not even that high. Most of the air sits within the first 10 kilometers, a layer of soft breathing thinner than the skin of an apple compared to the apple itself. The atmosphere is enormous in human terms, and gentle and thin all at once. Walk gently around the planet now. The circumference of the Earth at the equator is about 40,000 kilometers. 40 million meters. A number that comes out neatly because the modern meter was once defined so that this circumference would be exactly 40,000 kilometers, a soft, mathematical convenience that has since been refined by more careful measurement, but only slightly. If you could walk steadily, never sleeping, never stopping, you could circle the planet in perhaps 2.5 years. A jet aeroplane, flying at the slow, patient speed of a long-distance flight, can circle the planet in about 40 hours of steady flying. A radio signal, traveling at the speed of light, can circle the planet 7.5 times in a single second. The Earth is enormous to a walker, comfortable to an aeroplane, small to light. Each of these is a different way of holding the size of the same world. The Earth has a weight, too, a mass, more properly that is enormous and gentle at the same time. The whole Earth, all 6 octillion kilograms of it, all the mountains and the seas and the slowly drifting plates of rock and the long deep mantle beneath them, weighs about 6 septillion kilograms. A 6 followed by 24 zeros. a number too large to picture clearly. And yet, in the family of rocky planets in our own solar system, the Earth is not the largest. It is not the smallest. It sits gently, somewhere in the middle. And in the wider catalogue of worlds we know about, scattered around other stars, the Earth is one of the smaller, round things outsized, in most of the discovered systems, by larger super-Earths and gas giants, and the steady, distant glow of stars themselves. The Earth is large enough to hold an atmosphere, large enough to keep oceans liquid, large enough to drift in slow, quiet orbit around a small, ordinary star. But it is not, on the scale of worlds, especially big. The day is the most familiar rhythm of the planet. The Earth turns once on its axis every 24 hours or so. As it turns, the surface at the equator is moving at about 1,500 kilometers per hour, far faster than any jet aircraft has ever flown. The motion does not feel like motion, because everything you can see is moving with you. The atmosphere is moving with you. The buildings are moving with you. The trees are moving with you. The blood in your hand is moving with you. The Earth's turning is one of the slowest, gentlest, most unnoticed kinds of motion the universe contains. And yet, by the standards of human travel, it is fast. Around the planet, at a slow distance that is gentle on the human scale, but enormous on the scale of buildings, drifts the moon. The moon is the next quiet step outward in this video. It is about 384,000 kilometers away from the Earth. On average, about 30 Earths placed end to end. That is a strange and gentle number to picture. If you imagine a small line of 30 round Earths, each one 12,700 kilometers across, stretched out in a long row, the moon would sit at the far end of that row. In between, in that long stretch of soft space, there would be enough room for every other planet in the solar system, lined up end to end, with a little left over. The Earth-Moon system is small on the scale of the solar system, but it is enormous on the scale of anything humans have ever built. The Moon itself is about a quarter of the size of the Earth, about 3,400 kilometers across. About a quarter the size, but only about 1/80th the mass, because the Moon is made of slightly less dense rock and has no large iron core like the Earth's. The Moon turns slowly on its own axis, but it turns at exactly the same rate as it goes around the Earth, so the same face is always quietly turned toward us. The far side of the Moon was, for almost all of human history, the only large surface in the night sky that no one had ever seen. The familiar face, the soft pattern of bright highlands and dark seas of cooled lava that some cultures see as a face, some as a rabbit, some as a quiet human shape lying on its back, is the only face the Moon ever shows. Light makes the trip from the Earth to the Moon in just over a second. About 1¼ seconds, in fact. When you look at the Moon, the light you see has only just left it. A radio call from the Moon to the Earth, were anyone there to send one, would take about 1.25 seconds to arrive. Almost short enough for a conversation. Almost, but not quite. The first humans who walked on the Moon, decades ago, spoke with a quiet, noticeable delay back to the people on Earth. Words drifted across that gap in long, slow arcs, 1.25 seconds at a time. The Moon is the first companion. The Earth has only one large natural moon. Many planets in our solar system have dozens of small ones, but the Earth has just this single, slow companion, kept patiently in orbit by gravity. The two of them form the simplest possible pairing on the size ladder of tonight, a familiar planet and its quiet, slow companion, the closest natural body to home. A small system that can be drawn on a single sheet of paper with the Earth as a small round disk and the Moon as a smaller round disk, 30 diameters to the side. You are, in a quiet way, always on the Earth. The Earth is, in a quiet way, always in motion. The atmosphere holds you. The Moon, far above, traces its long, slow orbit. And as you settle into the next stretch of this video, let your awareness drift just a little outward, past the rooms of your home, past the cities and the seas, past the soft curve of the planet, past the thin layer of the atmosphere, into the soft space where the Earth and Moon turn together as a pair. That is the first big room. The next room will be larger still. Step outward from the Earth-Moon pair, and the next thing you meet, gentle and bright and immense, is the Sunday. The Sun is the first object in tonight's walk that is too large to hold easily in the imagination as a single piece. And yet it is also, paradoxically, the first object in tonight's walk that you have been quietly familiar with your whole life. You have felt it on your skin. You have seen it rise and set. You have watched it color the soft edges of clouds at the end of long days. The Sun is the friend at the door of the room of the solar system. Tonight we widen the room one more step and let it in. The Sun is about 109 times the diameter of the Earth. If the Earth were a small marble lying on a table, the Sun would be a small exercise ball on the other side of the room. To carry that comparison a little further, if the Earth were a glass marble about 2.5 centimeters across, the Sun would be a sphere a little over 2.5 meters across, taller than a person, taller than most doorways. Inside the Sun's volume, you could fit roughly 1.33 million Earths, packed gently together. It is hard to picture a million Earths. It is easier to picture this. The Sun is large enough that a small grain of sand dropped at its center would have to be lifted across nearly 700,000 kilometers of soft hydrogen and helium plasma before it reached the surface and emerged into space. The Sun contains about 99.8% of all the mass in the solar system. The rest of everything, every planet, every moon, every asteroid, every comet, every grain of dust drifting in slow orbit adds up to less than 0.2% of the system's total mass. The Sun is the great, quiet weight that holds the whole family together. The planets, including the Earth, are the smaller, round companions. The smaller, round companions are themselves enormous on the human scale, and gentle on the scale of the star they are bound to. The Sun's surface, the part we see when we glance at it through a low haze or when the daylight is softened by clouds, is about 5,500 degrees Celsius. Hot, but not the hottest part of the Sunday. Above the surface, in a strange and slow inversion that is still being patiently understood, the Sun's corona, the soft, pearly outer atmosphere, visible during total solar eclipses, climbs back upward to temperatures of a few million degrees in places. The exact mechanism is not entirely settled. It seems to involve magnetic fields, slow heating, and the constant turbulent motion of plasma. The Sun has not given up all of its secrets, even after all the slow, patient watching humans have done. The Sun is the place where the next ruler of the night appears, gentle and quiet. The Earth orbits the Sun at a distance of about 150 million kilometers. That distance is, in a way, the most important ruler of all of astronomy, because it is so often used as the natural unit for the wider solar system. We call this distance an astronomical unit. 1 astronomical unit. 1 AU. The distance from the Earth to the Sunday. From this point onward in the night, every other planet in our system will be described in terms of how many astronomical units it sits from the Sunday. Light, the slow, patient companion at every rung of this ladder, takes about 8 minutes and 20 seconds to travel 1 astronomical unit. That means the sunlight that lands on your closed eyelid tonight left the surface of the sun more than 8 minutes before you noticed it left. In fact, before you began this sentence. The sun you would see, if you looked up at it now during daytime, is the sun as it was a little over 8 minutes ago. The now of the sun and the now of the earth do not quite match. They are connected by light, and light takes time. From the sun, step outward through the family of planets. The first is Mercury, the smallest of the major planets, about 1/3 of an astronomical unit from the Sunday. Mercury orbits the Sun in just under 3 Earth months, a small, dense, rocky world with a slow rotation, a heavily cratered surface, and almost no atmosphere to soften the contrast between its scorching day side and its frigid night side. In the few permanently shadowed craters near its poles, where sunlight has never reached for billions of years, there are pockets of water ice, very quietly waiting. Mercury, in spite of being the closest planet to the Sun, has some of the coldest places in the entire inner solar system, tucked into the long shadows of its quiet poles. The next planet outward is Venus, at about 7/10 of an astronomical unit from the Sunday. Venus is about the same size as the Earth, slightly smaller, only a little less massive, and yet its surface is almost unrecognizable. Beneath a thick atmosphere of carbon dioxide, with clouds of sulfuric acid drifting through it, Venus runs a long, quiet greenhouse. The surface temperature is around 450 degrees Celsius, hotter than the day side of Mercury, even though Venus is much farther from the Sunday. The atmosphere is about 90 times the pressure of Earth's at the surface. And the planet rotates very slowly and backwards, so that a single Venusian day is longer than a Venusian year. The Sun, were you to stand on the surface beneath those acidic clouds, would rise gently in the west and set gently in the east, taking many months to make the soft, round trip. Almost everything about Venus is a slow and patient kind of strange. Next outward is the Earth, at 1 astronomical unit, the place we have just stepped away from. From here, we look back, a small blue and white sphere, mostly ocean, with 1 large pale companion drifting beside it. Then Mars, at about 1.5 astronomical units, smaller than the Earth, rust-colored, dry, with a thin atmosphere that is almost entirely carbon dioxide. Mars carries a great mountain on its surface, called Olympus Mons, that is taller than any mountain on Earth, almost 22 kilometers high, more than twice the height of Everest. Mars also carries a long, deep canyon, Valles Marineris, that would, if placed on Earth, stretch nearly across the entire continent of North America. Mars is small, but it carries the largest single mountain and the longest single canyon of any world humans have ever directly explored. From Mars, the Sun looks about 2/3 the size it does from Earth, slightly smaller, slightly softer, but still recognizably the Sunday. A sunset on Mars is blue, not red, because of the way the fine dust in its atmosphere scatters light. A sunrise on Mars is also blue. The Martian sky in daytime is, in a strange and beautiful inversion, a soft butterscotch color. Even on a small dry world, the sun continues to color the air softly in its own quiet way. Beyond Mars, the inner solar system gives way to the asteroid belt, a thin, wide ring of rocky and icy bodies, sitting roughly between 2 and 3 astronomical units from the Sunday. The asteroid belt sounds, in cartoon imagination, like a crowded, dangerous place. In reality, it is almost entirely empty space. The total mass of the asteroid belt is less than 4% of the mass of the Moon. The pieces are small, the gaps between them are enormous, Spacecraft pass through the belt easily, and the chances of any small spacecraft accidentally striking even a modest asteroid are vanishingly small. The largest body in the belt is a dwarf planet called Ceres, about 1,000 kilometers across, roughly a quarter the size of the Moon. Next come a small group of larger asteroids, Vesta, Pallas, Hygiea, and then a vast quiet population of smaller and smaller pieces, down to grains of dust drifting on slow circular orbits. A spacecraft on a fast trajectory, leaving the Earth in the right direction, takes about 6 months to reach Mars. About a year and a half to reach the inner edge of the asteroid belt. About 5 years to reach Jupiter, the next great planet outward. About 7 years to reach Saturn. About 9 or 10 years to reach Pluto, the small icy dwarf planet that orbits at the outer edge of the system. The slow, patient travel times of robotic spacecraft are themselves a quiet measure of how the room widens beyond the small inner block of rocky worlds into the much larger outer rooms. Light reaches Mars in about 12 minutes when the two planets are on the same side of the Sun, and about 22 minutes when they are on opposite sides. A command sent from a control room on Earth to a small spacecraft on Mars takes those 12 or 22 minutes to arrive. The spacecraft answers, and the answer takes another 12 or 22 minutes to come back. So conversations across the inner solar system are not really conversations. They are slow letters, sent and received with a patience that the Earth's own internet has all but forgotten. The inner solar system, the rocky worlds and asteroid belt room, is gentle and small compared to what comes next. It fits, generously, inside a sphere about 6 astronomical units, across 6 times the distance from the Earth to the Sunday. About 900 million kilometers from edge to edge. About 50 light minutes from edge to edge. Light could cross the whole inner solar system in less than an hour. It is still a tiny room, on the scale of the night. And yet, in this small room, almost everything we have ever directly built is contained. Every probe, every lander, every rover, every astronaut. Every footprint, every wheel track, every photograph of a tan landscape under a butterscotch sky. The first big room beyond the Earth is the inner solar system, and it is still small enough that human-built machines have walked it. The next room widens further, where the planets become enormous, and the year of an orbit becomes a long, quiet decade. Step gently with me. The room widens again. Beyond Mars and the asteroid belt, the room widens again, and the planets become enormous. Jupiter, the first of the 4 great outer worlds, orbits the Sun at about 5 astronomical units. 5 times the Earth-Sun distance. A flight of light from the Sun to Jupiter takes about 43 minutes. A radio command sent from Earth to a small spacecraft near Jupiter takes nearly an hour to arrive when the 2 planets are at their closest, and more than an hour and a half when they are on opposite sides of the Sunday. Already, just at this rung, conversations across the room of the solar system become long, quiet letters. Jupiter is the largest planet in the solar system by a wide margin, about 11 times the diameter of the Earth, and more than 300 times the Earth's mass. Inside Jupiter's volume, you could fit roughly 1,300 Earths, packed gently together. Jupiter is so large that, if you added perhaps 80 more Jupiters in mass, it would begin to fuse hydrogen in its own quiet core and become a small dim star in its own right. Jupiter, in some real sense, is the planet that almost became a sun. It is the soft, remembered ghost of a second star that never quite ignited. Jupiter's atmosphere is a slow, patient weather pattern of enormous bands and swirling storms. The bands, the soft, alternating cream and orange stripes, are the visible signature of jet streams that run all the way around the planet. The storms drift through them in slow, elegant patterns. The Great Red Spot, an enormous oval storm large enough to swallow the Earth, has been turning steadily for at least 400 years that humans have watched it through telescopes. Other storms come and go. The atmosphere does not have a solid surface. The soft yellow-cream cloud tops give way deeper down to hydrogen and helium in increasingly strange phases, until eventually, in the deepest interior, the hydrogen behaves as a kind of metal, conducting electricity through the slow churn of pressure. Around Jupiter, in slow, steady orbit, are dozens of moons. The four largest Io, Europa, Ganymede, and Callisto, are large enough to be small worlds in their own right. Io is racked with volcanism, its surface constantly resurfaced by sulfur eruptions that paint it in soft yellows and oranges. Europa is covered with a smooth shell of water ice, beneath which a slow, patient, global ocean of liquid water is thought to drift, kept liquid by the soft tidal heat of Jupiter's gravity. Ganymede is the largest moon in the entire solar system, larger than the planet Mercury, and is the only moon known to generate its own magnetic field. Callisto, the outermost of the four large moons, is one of the most cratered surfaces ever found, a frozen archive of impacts, stretching back nearly to the formation of the solar system itself. Step outward again. Saturn, the next great planet, orbits the Sun at about 10 astronomical units, twice as far as Jupiter, 10 times farther than the Earth. A flight of light from the Sun to Saturn takes about 80-15. The room has widened further. Light, which crosses the inner solar system in less than an hour, now takes more than an hour just to reach Saturn from the Sunday. Saturn's bright ring system, made of countless small bodies of ice and rock, ranging in size from grains of dust to mountains, stretches outward from the planet for about 280,000 kilometers wider than the entire Earth-Moon distance. And yet, in spite of being wider than the distance from the Earth to the Moon, the rings are, in places, only 10 or 20 meters thick, thinner in proportion to their width than a sheet of paper. From the side, edge on, the rings nearly vanish. From above, they form one of the most beautiful structures in the visible universe. Around Saturn drift many moons. The largest is Titan, about the same size as Mercury, wrapped in a thick orange atmosphere of nitrogen and methane. On Titan, the soft cold drizzle that falls is not water but methane, and the slow rivers and lakes that have been mapped on its surface are likewise liquid methane rather than water. The hydrological cycle of Titan is the only known hydrological cycle other than Earth's, and it runs on a chemistry of small, soft hydrocarbons rather than water. Another moon, Enceladus, fires geysers of water and dissolved salts and small organic molecules out into space from cracks near its south pole, the soft, visible evidence of a global subsurface ocean held liquid by tidal heat. Uranus orbits at about 20 astronomical units, twice as far as Saturn, 20 times the Earth-Sun distance. A flight of light from the Sun to Uranus takes about 2.5 hours. Uranus is an ice giant, smaller than Jupiter or Saturn, but still about 4 times the diameter of the Earth. It has a curious, quiet tilt. Its axis lies nearly on its side, so that as Uranus orbits the Sun, each pole takes a turn pointing almost directly at the star, with the other pole turned almost directly away. The Uranian year is about 84 Earth years long, which means that for each pole, summer and winter are each about 42 Earth years of continuous daylight and continuous darkness in turn. The slow patience of an Uranian season is unlike anything we are used to. Neptune orbits at about 30 astronomical units, 30 times the Earth-Sun distance. A flight of light from the Sun to Neptune takes about 4 hours. Neptune is about the same size as Uranus, also an ice giant, with a soft blue color from methane in its atmosphere, and the fastest steady winds in the solar system, gentle to look at, but supersonic by the standards of the Earth's air. A Neptunian year is about 165 Earth years. Since Neptune was first discovered by telescope, in modern terms, it has only just completed a single orbit around the Sunday. Triton, Neptune's largest moon, orbits in the opposite direction from Neptune's spin. A quiet hint that Triton was once a wanderer, captured by Neptune's gravity, rather than a moon born in place alongside the planet. From Neptune, the Sun is a bright pinpoint of light. Only about 1,000th as bright as it is from Earth, still vastly brighter than any other star in the Neptunian sky, still the unmistakable center of the system, but small enough to be covered easily by a fingertip held up at arm's length. A spacecraft near Neptune, looking inward, would see a small, bright star, and, if its instruments were sensitive enough, a tiny, pale blue speck, a few degrees away from the star, the Earth, the home, a soft point of light in the dark. The whole region of the planets, from the Sun out to Neptune, fits gently inside a sphere about 60 astronomical units across. About 60 times the distance from the Earth to the Sunday. About 8 light hours across. That is enormous by the standards of human travel. It is small, still, by the standards of the night we have ahead of us. Beyond Neptune, the Kuiper Belt begins. It runs roughly from 30 to 50 astronomical units, a much wider ring than the inner asteroid belt and made of much icier material, small worlds of frozen water, methane, ammonia, and rock. Pluto orbits inside the Kuiper Belt, at an average distance of about 40 astronomical units from the Sunday. Sunlight at Pluto is more than 1,500 times dimmer than it is on Earth. Bright enough to read by, but only just. The brightest part of a Plutonian day is dimmer than a soft summer twilight on the Earth. Pluto has a thin atmosphere of nitrogen that freezes and falls to the surface as Pluto's elliptical orbit carries it through its long winter and slowly sublimates back into gas as the small dwarf planet returns to its warmer summer regions. Other dwarf planets share the Kuiper Belt, Eris, Makemake, Haumea, and many smaller bodies. Some of them, like Sedna, follow long, stretched-out orbits that take them hundreds of astronomical units out at their farthest. Sedna's orbit reaches almost 1,000 astronomical units from the Sun, at its farthest point, far beyond the Kuiper Belt, far beyond the soft outer edge of the system as it was understood for most of the 20th century, and yet still, in its own quiet way, bound to the Sun by gravity. Beyond Sedna, beyond the Kuiper Belt, but still under the soft hold of the Sun's gravity, lies the heliopause. The heliopause is the gentle boundary where the solar wind, the steady, patient stream of charged particles flowing outward from the Sun, finally slows to a stop against the soft wind that flows in from other stars. The heliopause sits roughly 120 astronomical units from the Sunday. A few human-built spacecraft, on slow, patient outbound trajectories that began decades ago, have already crossed this threshold and are now drifting in the soft, thin gas of the interstellar medium. These are the only human-made objects ever to have left the soft wind of the Sun behind. Beyond the heliopause, the Sun's gravity still reaches outward. Far outward. Out to a great, quiet, spherical shell called the Oort Cloud, a vast, diffuse reservoir of icy bodies thought to begin a few thousand astronomical units from the Sun, and to extend, perhaps, to 100,000 astronomical units away. The Oort Cloud has never been directly imaged. It is so vast, and the bodies in it are so small and so cold and so widely scattered that most of it is inferred rather than seen. We know it must exist because of the long-period comets that occasionally fall in from very nearly any direction in the sky, gently jostled inward over deep time by the slow gravity of nearby stars, passing in their own slow walks through the galaxy. The Oort Cloud may contain 1 trillion icy bodies or more, drifting silently through the dark at the soft outer edge of the Sun's family. 100,000 astronomical units is roughly 1.5 light-years. The Sun's gravity finally loses its quiet hold somewhere around 2 light-years out, where the soft pull of nearby stars begins to win. So the whole soft home of the Sun, the planets, the belt, the heliopause, the Oort Cloud fits inside a sphere about 3 light-years across. Light, traveling outward from the Sun, takes about a day to reach the heliopause. About a few months to reach the inner edge of the Oort Cloud. About 1.5 years to reach the cloud's outer edge. A spacecraft on a current outbound trajectory would not reach the inner edge of the Oort Cloud for several centuries. The outer edge for nearly 30,000 years. We are, at this stage of the night, just barely stepping past our own front door. The nearest other star is still a few rungs of the ladder away. Let the slowness settle. Let the room widen, very gently. The Sun is now a small, bright lamp in a very large, dark hall, and we are still inside that hall, walking outward. Step gently past the soft outer edge of the Sun's gravitational hold, and the room widens into the stretch of dark between the stars. The ruler changes here. Astronomical units, those quiet steps of 150 million kilometers, begin to feel small. The galaxy uses a larger unit. The galaxy uses the light year. A light year is the distance that light travels in a single year. Light moves at almost 300,000 kilometers every second, fast enough to circle the Earth 7.5 times in a heartbeat, fast enough to cross the inner solar system in less than an hour, fast enough that the Sun's light reaches Earth in just over 8 minutes. And yet, even at that speed, light takes 1 year of patient travel to cross a single light year. About 9.5 trillion kilometers. About 63,000 astronomical units. The light year is a unit that holds, inside it, both a distance and a time. Every step we take outward from here is also a step backward into the past. To look 1 light year out is to see something as it was 1 year ago. The night sky, at the scale of stars, is always a quiet archive. The next nearest star to the Sun is called Proxima Centauri. It sits about 4.25 light-years away. Light leaves Proxima Centauri now, and it arrives at Earth in a little over 4 years. Long enough that a child born tonight beside whomever is listening to this video would be a small toddler before the light of that nearest other star reached this room. A small dim red dwarf, far less massive than the Sun, far cooler at its surface, far longer lived in the slow, patient way that small red stars endure for trillions of years. Around Proxima Centauri, in close orbit, drifts at least 1 rocky planet, perhaps more than one. The closest other star to ours has its own family of worlds. Just beyond Proxima Centauri, slightly farther out, are 2 larger stars that orbit each other in a slow, close pair. They are called Alpha Centauri A and Alpha Centauri B. Together with Proxima Centauri, they form a small triple system, the nearest 3 stars to our own. From any of the worlds in that small system, the Sun would appear as a single bright star, much like the way Alpha Centauri appears in our own night sky. Barnard's star, a small, fast-moving red dwarf, drifts at about 6 light-years from the Sunday. It moves quickly across the sky, by the slow standards of stellar motion quickly enough that over a human lifetime, its position against the background of more distant stars shifts noticeably. Most stars seem to stand still in the sky. Barnard's star does not. Barnard's star is one of the soft reminders that every star you see, including our own Sun, is moving, that the sky we know is, at every moment, very slowly rearranging itself. Wolf 359 sits about 7.5 light-years away. Another small red dwarf, smaller than the Sun, dim enough that you cannot see it with the unaided eye even on the clearest, darkest night. Lalande 21185 lies a little farther, also small and dim. Together with Barnard's star, Wolf 359, and the Alpha Centauri triple, these make up most of the immediate solar neighborhood. Sirius, the brightest star in the entire night sky as seen from Earth, lies a little less than 9 light-years away. Sirius is large and hot and luminous, about twice the mass of the Sun, about 25 times as bright. Sirius is also a binary star. A bright white dwarf orbits gently around it. The bright Sirius we can see, and the small dim Sirius B that orbits it together form a slow, elegant pair, the closer of which has been the brightest single point of light in the human night sky for as long as anyone has been here to watch it. Sirius does not move quickly across our sky. Its rising and setting through the seasons has been used as a calendar by cultures for thousands of years. The brightest star is also, in human terms, the most reliable. Within a sphere 10 light-years across, centered on the Sun, there are only about a dozen known stars. The Sun's immediate neighborhood is, by the standards of the galaxy, very quiet. Stars are not packed shoulder to shoulder. They drift through the dark, with enormous distances of soft, empty space between them. Every one of them moving in its own slow, patient orbit, every one of them holding its own family of planets and dust and quiet gravity. Widen the sphere a little. Within 30 light-years, the count of known stars grows to a few hundred. Most of them are smaller and dimmer than the Sunday. Most of them, in fact, are red dwarfs, the small patient stars that, in the deep future, will outlive all the larger stars by a wide margin. The red dwarfs are the most common kind of star in the galaxy, by far. They are also the dimmest. The bright stars we name in stories the giants, and the very hot blue stars, are a very small minority, even though they dominate the visible night sky. Widen further. Within 100 light-years of the Sun, a small sphere that is still, in the language of the galaxy, very local, there are tens of thousands of stars. Among them, careful observation has revealed many planetary systems. Planets, it has slowly become clear, are not rare. Almost every star in the galaxy is likely to host at least one planet. Many host more than one. Some host elaborate small families of rocky worlds, ice worlds, and gas worlds. Worlds, by the count of the universe, outnumber stars. There are more planets in the galaxy than there are stars to gather them. The brightest stars in the night sky are not always the nearest. Some of the most familiar stars, the ones whose names have been remembered through long cultural histories, are not in our immediate neighborhood at all. They are giant suns shining from hundreds or thousands of light-years away, sending their bright light across the long, quiet dark. Their light has been traveling for hundreds of years before reaching the eye of anyone who looks up tonight. Some of the stars in the most familiar constellations are even farther, many thousands of light years out, their light older than the oldest cities humans have built. The night sky is, in this sense, a quiet archive of light from many different distances and many different times. Every star you see is at its own depth in the past. The constellations themselves are slowly changing. Over very long timescales, the patterns that people in any one century recognize as familiar shapes a hunter, a bear, a dipper, a cross, a small dog are slowly drifting apart. The stars within each constellation are moving in their own directions around the center of the galaxy at their own speeds. In 50,000 years, the patterns of the sky will look slightly different. In 1,000,000 years, they will be unrecognizable. The shapes you saw as a child, the shapes your grandparents saw, the shapes the oldest skywatchers saw, all of these patterns are stretched moments inside a much longer, slow drift. The sun itself is part of that drift. The sun is moving at about 200 kilometers every second through space, on a long, slow orbit around the center of the Milky Way. That orbit takes it slowly through different regions of the galaxy, sometimes through denser clouds of gas and dust, sometimes through quieter, empty stretches. The motion is so slow, by the standards of a human life, that you do not feel it. But over millions of years, the sun has carried the Earth and the Moon and all of the planets through entire different neighborhoods of the galaxy, against entirely different backdrops of stars. When you look up at the sky tonight, the stars you see are not where they will be in 1,000,000 years. They are not even where they were when their light first left them. They are at their soft, long depth in the past, sending you the picture of a sky that is, very slowly, becoming something else. The night sky is a slow-motion photograph of a system that is gently rearranging itself, one orbit at a time. Within a few hundred light years, there are millions of stars. Within a few thousand, tens of millions. The numbers grow rapidly as the sphere widens. And yet, even at these scales, we are still entirely inside the home galaxy. We have not yet stepped into any other galactic room. The Milky Way is the next great soft ruler of the night. The room widens once more. Before we step into the home galaxy, settle gently in the local stellar neighborhood for a moment longer. The sun's quiet, immediate surroundings carry a few softer details that are worth hearing before the room widens further. The stars in our immediate neighborhood are not all moving in the same direction. Each one is on its own slow orbit around the center of the galaxy, and over hundreds of thousands of years, the relative positions of our neighbors slowly change. Proxima Centauri is currently moving slightly closer to the Sunday. In about 30,000 years, it will be slightly nearer than it is now, before beginning to drift away again. Other stars, now somewhat farther away, will, over similar timescales, pass closer to the Sun than Proxima ever does. The title of nearest star to the Sun is, in this very long way, gently passed back and forth between neighbors over hundreds of thousands of years. Some of those future near neighbors are known by name. Gliese 710, a small dim star currently about 60 light-years away, is slowly approaching the Sun on a long, quiet trajectory. In about 1,000,000 years and a quarter, it will pass within a single light-year of the Sun, much closer than Proxima Centauri is now. It is small enough and far enough away that its passage will not seriously disturb the Sun's family of planets, but it may gently stir some of the outer reaches of the Oort Cloud, perhaps sending a soft scattering of new long-period comets falling inward toward the inner solar system over many tens of thousands of years afterward. By that time, the Earth's continents, climate, and inhabitants will be so different from now that the slow rearrangement of the outer Oort Cloud will be only a quiet footnote on a much larger story. The night sky, in a million years, will not look quite like it does tonight. Some of the brightest stars will have drifted closer, becoming brighter still. Others will have drifted farther, becoming dimmer. New stars, now too faint to see, will have edged into view. The whole soft pattern of the night will, very gently, have rearranged itself. Constellations as cultural shapes will have shifted into something else. We are, at every moment, inside this slow, soft drift. The neighborhood is large, but it is not still. The stars are not pins on a fixed sky. They are slow, patient travelers, every one of them, and the sky tonight is only the soft sum of where they happen to be along their long, quiet orbits at this particular moment in the Milky Way's slow turning. Step outward again. The ruler changes once more from light years to thousands of light years, and from individual stars to the great wheel that they are arranged within. The next room is the home galaxy, the Milky Way. Almost everything any human eye has ever seen in the night sky belongs to it. The Milky Way is a flattened wheel of stars, about 100,000 light years across. It is hard to picture that number, so let it widen slowly. A single light year is already a distance that light takes a year to cross. 100,000 of those, lined up end to end, would still all fit inside the Milky Way. The galaxy is large enough that, even at the speed of light, would take a single beam 100,000 years to cross from one rim to the other. The Milky Way is shaped like a thin disk with a softly bulging center. The central bulge is about 10,000 light years across older stars, redder stars, packed more densely. The disk where most of the bright young stars live is much thinner than it is wide, only a few thousand light years thick. If you could see the Milky Way edge on from far enough away, it would look like a glowing dinner plate floating in the dark. From above, it would look like a great soft pinwheel. The Milky Way is a barred spiral, which means that the central bulge is slightly elongated into a long, quiet bar of stars, and the spiral arms extend outward from the two ends of that bar. The Milky Way has several main spiral arms. The Sun does not live on one of the major arms. The Sun lives on a smaller spur, called the Orion spur, set between two of the larger arms. We are not in the most crowded part of the disk. We are in a softer, quieter side street. The Sun lives about 26,000 light years from the center of the galaxy, about a quarter of the way out from the galactic core to the edge of the disk. From this comfortable middle distance, we look out at the spiral arms and the soft, glowing pattern of the home galaxy. On a clear, dark night, far from city lights, the Milky Way is visible to the unaided eye as a soft band of light stretching across the sky. That band is the combined glow of countless stars in the plane of the galactic disk. When you look at the Milky Way in the sky, you are looking along the disk of your own home galaxy, with your eye following the long, quiet street of stars off into the distance. The Milky Way contains somewhere between 100 billion and 400 billion stars. The number is hard to pin down, precisely because most of the stars in the galaxy are small, dim red dwarfs, far below the limits of any one telescope's ability to fully catalogue. But somewhere in that range, 100 billion, 200 billion, maybe 400 billion, more stars than there are seconds in 3,000 years. More stars than there are grains of sand on a long, quiet beach. Most of those stars are small red dwarfs, gentle, low-mass, slow-burning suns that will keep shining quietly for trillions of years longer than the lifetime of any larger star. The bright giants we name in stories, the blue supergiants, the red supergiants, the bright white suns, are a tiny minority of the galaxy's population. The bulk of the galaxy is gentle and small. The bulk of any starry night is, in a quiet way, dim companions far outnumbering bright ones. The Sun, our own ordinary yellow star, sits gently somewhere in the middle of the size and brightness distribution. There are many stars smaller and dimmer. There are also many stars, larger and brighter. The Sun is a quiet, ordinary citizen of a quiet, ordinary spur, in a quiet, ordinary spiral galaxy, in a long, quiet universe. It carries us. It carries all the slow, patient business of life on Earth. And it is one of hundreds of billions in this single room. The Sun is moving. The Sun is orbiting the center of the galaxy at about 200 kilometers every second. That is a much faster speed than anything on a human scale. And yet, because the orbit is so vast, a single full circuit around the center of the Milky Way takes the Sun about 225 to 250 million years. One full orbit. One galactic year. A galactic year is so long that, in the entire history of complex life on Earth, the Sun has completed only a few dozen of them. The dinosaurs lived about 3/4 of a galactic year ago. The first humans appeared in the last small fraction of one. The whole of recorded human history, from the earliest writing through the most recent moments of this evening, has occupied less than 1,000th of a single galactic year. The slow turning of the Milky Way is so slow that no civilization will ever see it complete an orbit. We see only a small, soft fragment of one slow turn. The Milky Way is mostly empty space. If the Sun were a single grain of sand placed somewhere in a city, the next nearest star, Proxima Centauri, would be another single grain of sand many city blocks away. And between those two grains of sand, the city would be otherwise nearly empty. Galaxies look full of stars from the outside because we see only the brightest combined glow, but in fact, they are made mostly of soft, dark space, with patient bright points of light scattered very thinly through it. Between the stars, the galaxy is full of soft, slow clouds of gas and dust, the nebulae from which new stars are still being born, and into which old stars eventually exhale themselves. Some of these clouds are bright and famous, glowing softly red or blue in long-exposure photographs. Others are quiet and dark, vast, dim regions of soft molecular hydrogen, slowly collapsing under their own weight, slowly forming the next generation of stars. The galaxy is constantly making more of itself. The slow, patient business of star formation has been continuing, somewhere in the Milky Way, every moment for billions of years. At the center of the Milky Way sits a supermassive black hole. We call it Sagittarius A star. It has the mass of about 4 million suns. By the standards of supermassive black holes, it is small. The largest known supermassive black holes are millions or even billions of times larger. But by any human standard, it is enormous. 4 million suns packed into a region perhaps the size of the orbit of one of the inner planets of our own solar system. Yet compared to the entire galaxy, Sagittarius A star is a small, soft anchor. Its gravitational reach extends only a few light-years out, while the galaxy itself stretches 100,000 light-years across. The Sun, in its long, slow orbit, does not feel Sagittarius A star directly. The Sun feels the combined gravity of the entire mass of the galaxy, most of which is dark matter, an invisible kind of mass that does not interact with light, but does interact gravitationally and does help hold the galaxy together. The Milky Way is held together not by the gravity of its visible stars alone, but by a much larger halo of dark matter invisible to telescopes, yet binding the galaxy and shaping its rotation. The dark matter halo reaches outward, perhaps 500,000 to 1 million light-years from the center, far beyond the bright disk, into the empty dark. If the Milky Way were the size of a continent, the visible stars would form a thin glowing crescent across it, and a much larger sea of unseen matter would surround them, the soft, slow weight that keeps the disk turning together. The galactic year is the heartbeat of the home galaxy. The Sun makes one slow orbit, and another, and another. The Earth turns once a day. The Earth orbits the Sun once a year. The Sun orbits the center of the galaxy once every 250 million years. Each scale has its own clock. Each clock is slower than the one before. And all of them, together, are running at the same time, quietly, every moment, even now, while you settle deeper into the soft pace of this video. We live in the slowly turning home. The home is enormous. The home is gentle. The home is one room of many, one rung of a much longer ladder. And beyond the home galaxy, the next room widens further. The next ruler is millions of light years, not thousands. Step gently with me. The local group is waiting. Settle for a moment before we step outward again into the quiet inside of the home galaxy. The Milky Way is enormous, but it is also full of slow, patient details, and it is worth lingering with them gently before the room widens further. Between the spiral arms, the disk of the Milky Way contains many smaller features. There are open clusters, where a few hundred to a few thousand young stars sit gently together, recently born from the same parent cloud, slowly drifting apart over hundreds of millions of years. There are globular clusters, much older, much denser, much more spherical, soft, tight, groups of hundreds of thousands or even millions of stars, orbiting in long, slow paths through the galaxy's outer halo, far above and below the plane of the disk. Some of the globular clusters are nearly as old as the galaxy itself. Some hold stars that formed in the very first chapters of the Milky Way's life. The disk of the galaxy is gently warped at its outer edges, slightly tilted upward on one side and downward on the other. The warp is gentle but real, the soft, slow signature of the gravitational pull of the Milky Way's nearby small satellite galaxies and of the larger drift of the local cosmic web. The galaxy is not a perfectly flat disk. It is a softly tilted disk, gently bending at its edges, slowly turning through a much larger landscape. Within the disk, there are vast stretches of nearly empty space between stars. There are also long, quiet streams of stars from small satellite galaxies that the Milky Way has been gently absorbing over the past several billion years. The Sagittarius dwarf galaxy, for example, is currently being slowly torn apart by the gravity of the Milky Way, its stars stretched into a long, quiet stream that wraps around our galaxy in a soft loop. The Gaia Space Telescope and other instruments have, over the past few years, slowly mapped these streams in beautiful detail. The Milky Way is a slow, patient assembler. It has been gently making itself, one small, absorbed satellite at a time, for billions of years. The center of the Milky Way is hidden from our direct view by enormous quiet clouds of dust along the plane of the disk. We cannot see Sagittarius A star with optical light from here. We can, however, see through the dust at other wavelengths, in infrared, in radio, in X-rays. The center of the galaxy is, in those wavelengths, a region of slow, patient activity, a swarm of stars orbiting the supermassive black hole at speeds of hundreds or even thousands of kilometers per second, with the closest of them completing a single orbit in only a few decades. The center is dense. The center is full. The center is quietly busy. And yet, in any single light, it remains gentle. Sagittarius A star itself is, by the standards of supermassive black holes, a very quiet one. It does not actively feed on much material. It does not pour out the bright, fierce light of a quasar. It simply waits, gently, at the center of the home. The Milky Way is part of a slow, ongoing story. The galaxy was not always this shape. It has been built up, over time, from the slow merging of many smaller galaxies and from the slow, patient accretion of gas from intergalactic space. The thick disk, a slightly puffier population of older stars, sitting above and below the thin disk where the Sun lives, is thought to be the soft remnant of an earlier era, when smaller galaxies merged and stirred up the disk into a thicker form. The thin disk, where most of the bright young stars live now, formed slightly later, in a calmer, settled epoch, and has been the soft current home of newly forming stars for billions of years. Even now, the Milky Way is still slowly making new stars. The total rate is not large, only a few new stars per year, on average. But over the lifetime of the galaxy, those small, slow rates have added up. The stars you see in the night sky, and the many you cannot see, are the slow accumulation of billions of years of patient formation. Most of them are older than the Earth. Some of them are nearly as old as the universe itself. So when you look up at the soft band of the Milky Way in the night sky, you are looking at a slow, patient story of a galaxy assembling itself. You are looking at the home. You are looking at the room that contains the sun, the planets, the moon, the Earth, and the slow, patient body that is listening to this video. The home is enormous. The home is gentle. The home is one rung of a much longer ladder, and the room widens once more. Step gently outward from the Milky Way. The ruler changes again. Thousands of light years give way to millions. And the next room is not a galaxy, but a small, soft family of galaxies, the local group. The cluster the Milky Way belongs to. The local group is a small, loose cluster of about 80 known galaxies, gently bound to one another by gravity. They drift together through the wider dark, held in a slow, patient relationship that has lasted for as long as any of them have existed. Most of the members of the local group are small. Most are dwarf galaxies, each containing only a few million or a few 100 million stars. They are small, soft fragments compared to the Milky Way. Many of them are too dim to be seen, except with large telescopes and long, patient exposures. 3 of the local group's members are large spiral galaxies. The Milky Way is one of them. The second is Andromeda, the largest galaxy in the local group. The third is the Triangulum Galaxy, a smaller spiral that is the third bright spiral of the family. Andromeda is the nearest large galaxy to our own. It sits about 2.5 million light-years away. The light you see when you look at Andromeda has been traveling for 2.5 million years. It left Andromeda when our distant ancestors were just beginning to chip stone tools. It has been on its long, quiet journey across the dark for almost the entire history of human-like beings on Earth. When that light finally reaches an eye looking up tonight, it has been on the road since before language, before writing, before fire was reliably carried. The picture of Andromeda you can see is a quiet portrait of a galaxy as it was long, long ago. On a clear, dark night, far away from city lights, Andromeda is visible to the unaided eye. It looks like a small, soft smudge of light, about as wide as a few full moons placed side by side. It is, by far, the most distant single thing the unaided eye can see. Anything farther than Andromeda is too dim, too small, too softly spread to register without a telescope. Andromeda is the soft outer edge of what bare seeing can reach. Triangulum, the third bright spiral, is a little farther, about 3 million light-years away, and smaller than either the Milky Way or Andromeda. On very dark nights, with eyes that have had a long, quiet time to adjust to the dimness, some careful watchers can also see Triangulum as a faint blur. After Triangulum, the rest of the galaxies in the local group are below the threshold of unaided sight. The Magellanic Clouds, two small companion galaxies of the Milky Way, are visible from the southern hemisphere as soft, pale patches of light. The large Magellanic Cloud sits about 160,000 light-years away, and the small Magellanic Cloud about 200,000 light-years away. They are much closer than Andromeda. They are gentle satellites, drifting on long, quiet orbits around the Milky Way, like the moons of a planet, but on a vastly larger scale. From the southern sky, on a clear night, they look like soft, detached pieces of the Milky Way, hanging quietly in the dark beside it. The rest of the local group is made of small dwarf galaxies, some of them companions of the Milky Way, some of them companions of Andromeda. Each one is small and quiet, with only a small, soft population of stars and very little gas. Some have been gently absorbed into the Milky Way's halo over time, leaving streams of stars stretched out along their long, slow orbits. The Milky Way has been growing, very gently, for billions of years, by quietly drawing in smaller galaxies that drifted too close. The whole local group sits inside a region roughly 10 million light-years across. A tiny island, by cosmic standards, but already large enough that no light could cross it within a human lifetime. The room has widened enormously. From the soft city of the Milky Way, we have stepped into the soft neighborhood of galaxies, and even this neighborhood is too large for any single light beam to cross within the time of a human life. The local group is gravitationally bound. That is an important, quiet fact. The wider universe is expanding the great soft drift of cosmic expansion that we will come to in a few rooms from now. But inside the local group, the galaxies are bound to one another by gravity. They will not drift apart from one another. The members of the local group will stay together for as long as the universe keeps its current form. They are a small family, holding hands gently across the dark. Over billions of years, the Milky Way and Andromeda will slowly approach each other. The two great spirals are gently moving toward each other, very slowly, in a long, quiet approach that has been ongoing for as long as there have been galaxies. In about 4 to 5 billion years, they will begin to merge. And here is one of the gentlest facts of the night. When two galaxies merge, almost no individual star strikes another. Galaxies are so empty, so mostly dark, that two of them can pass right through one another like two flocks of birds crossing the same field. Each individual star has so much soft space around it that the probability of any single star running into any other single star during a galactic merger is, essentially, zero. The merger of the Milky Way and Andromeda will not be a collision. It will be a slow merging, a long, quiet rearrangement of stars over hundreds of millions of years, during which the two spiral disks gently dissolve into one larger, softer shape. By the time it is over, somewhere in the distant future, the two galaxies will have become a single larger galaxy. It will have a new shape, probably a rounder, more elliptical form, without the clean spiral arms of the original two. Some astronomers have given this future merged galaxy a soft name, Milkomeda. It is a name that hints both at the Milky Way and at Andromeda. A small, affectionate way of acknowledging that the two galaxies, given enough time, will become a family of two that became a family of one. The night sky, as seen from any surviving descendant world, will be slowly rearranged through this process. But it will be slow. Anyone who could watch it from beginning to end would have to watch for billions of years. No single night, no single life, no single civilization could ever observe more than a small fragment of it. The merger is unfolding now. There is no urgency in any of it. Even more recently, careful new measurements have softened the certainty of the merger. The exact path of Andromeda, its sideways motion as well as its approach, is now thought to be slightly less certain than it once was. There is some chance that the Milky Way and Andromeda will instead pass nearby each other rather than directly merging, and only meet again much later. The future of the two galaxies is more open than it was once said to be. The certainty has become a quiet, softer probability. The night gives us back its open door. Beyond the local group, the nearest small clusters of galaxies sit at distances of around 10 to 13 million light-years. The Sculptor group, the M81 group, the Maffei group, and a few others, each one a small, soft family of galaxies, much like our own local group, holding gently together by gravity. From here, the universe begins to show its quiet, repeated pattern. Galaxies in groups, groups in larger clusters, clusters arranged into larger, softer structures still. At these distances, light itself becomes a slow instrument of time travel. The deeper we look out, the further back into the universe's past we see. From 2.5 million light-years out, Andromeda shows us its picture from 2.5 million years ago. From 10 million light-years out, the Sculptor group shows us its picture from 10 million years ago. There is no other way to see things. Light is the messenger, and light is patient. To see the universe at all is to see its past, gently held in light. We have stepped out of the home galaxy. We are in the soft neighborhood of galaxies. The room widens again from here. The next ruler is hundreds of millions of light-years. The local group itself is only the beginning of a much larger pattern. Step gently with me. The clusters and the cosmic web are waiting. Step outward once more. The ruler now becomes hundreds of millions of light-years. At this scale, individual galaxies become small points of light, and the structures of interest are clusters of galaxies and superclusters of those clusters and the soft webs they are arranged into. The universe begins to show its slow, patient pattern at the largest scale. The Virgo cluster, the nearest large cluster of galaxies to us, lies about 55 million light-years away. It contains over 1,000 galaxies, drifting in a loose three-dimensional swarm. Many of them are large, bright galaxies, much larger than the Milky Way. At the soft center of the Virgo cluster sits an enormous elliptical galaxy called Messier 87, a great, quiet sphere of older stars, with a supermassive black hole at its center several billion times more massive than the Sunday. The black hole at the center of Messier 87 was, in fact, the first supermassive black hole ever directly imaged. The soft, round shadow of its event horizon, seen across 55 million light-years of dark, is a slow, patient achievement of careful astronomy. The local group itself, the small family of galaxies the Milky Way belongs to, is a small outlying member of the much larger Virgo supercluster. The Virgo supercluster is roughly 100 million light-years across, and it contains the Virgo cluster, the local group, and many other smaller groups of galaxies. We are not at the center of the Virgo supercluster. We are on its outskirts, a small, soft member quietly drifting along its edge. The Virgo supercluster, in turn, is one piece of a much larger soft structure called Laniakea. Laniakea is a Hawaiian word meaning immeasurable heaven, and it was chosen as the name for a vast network of galaxies that all flow together gravitationally. Laniakea contains about 100,000 galaxies and stretches some 500 million light-years across. It includes the Virgo supercluster, the Hydra Centaurus supercluster, the Pavo Indus supercluster, the Norma cluster, and many others. They are not all bound to one another the way the local group is. Laniakea is not a single tightly bound object, but the galaxies within it are gently flowing together, all drifting along in the same large, slow river of cosmic motion. Within Laniakea, the galaxies are gently flowing toward a region called the Great Attractor. The Great Attractor is a quiet gravitational center, partly hidden behind the dust and stars of our own Milky Way as seen from Earth, sitting some 250 million light-years away in the direction of the constellation Centaurus. We do not see it clearly. We feel it in the sense that the galaxies of our supercluster, including the Milky Way itself, are drifting toward it at hundreds of kilometers per second, in a slow, vast, collective motion through space. Beyond Laniakea, even larger soft structures stretch outward. The Perseus-Pisces supercluster lies some 250 million light-years from us, stretching across hundreds of millions of light-years. The Coma supercluster lies in another direction, anchored by the very large Coma cluster of galaxies. The Shapley supercluster, at about 650 million light-years away, may be the most massive nearby concentration of galaxies, a kind of distant senior partner of the soft local motion, a great quiet weight that influences the slow flow of everything around it. At these scales, the universe stops being a sea of galaxies and starts looking like a vast, soft web. Long filaments of galaxies thread through enormous, quiet voids. The filaments are narrow on a cosmic scale, but enormous on any other. They can stretch for hundreds of millions of light-years, with galaxies strung along them like beads on a long, quiet thread. At the soft junctions where filaments meet, the galaxies cluster more densely. Between the filaments, in the great voids, the galaxies are rare. Inside a void, you might travel for tens or hundreds of millions of light-years without finding a single bright galaxy. These cosmic voids can be tens or even hundreds of millions of light-years across. They are mostly empty space, not entirely empty, but very nearly so. The voids contain a thin haze of dark matter and a small scatter of dwarf galaxies, but the bright spiral and elliptical galaxies that make up most of the visible universe are almost entirely absent from them. From inside a void, the night sky would look stranger and quieter than it does from inside a supercluster. The constellations would be the same. Those are made of nearby Milky Way stars, but the soft glow of distant galaxies in long-exposure photographs would be sparser. The Boötes void, one of the largest known nearby voids, is about 330 million light-years across. A vast, quiet emptiness, with only a very small nucleus of galaxies found inside it. The Boötes void was first noticed because surveys of galaxy positions across a particular patch of the sky kept finding far fewer galaxies than the rest of the universe contained. The void had been there all along, of course. It simply needed the patient mapping of many galaxies before anyone could see its shape. Many other voids of similar size have since been found, scattered across the sky. The universe is made, at the largest scales, of these vast, soft, empty spaces interleaved with the slow, narrow filaments of galaxies threading through them. The cosmic web is the largest known pattern in the universe. Its filaments, walls, and voids reach across distances that would take light hundreds of millions of years to cross. It is a slow, soft, three-dimensional structure of galaxies arranged along the gravitational scaffolding of dark matter, like soft frost crystals along the strands of a hidden web. Where the dark matter is densest, the galaxies cluster. Where the dark matter is thinnest, the galaxies thin out and the voids open. The visible universe is, in a quiet way, a slow, patient frost on a great unseen scaffolding. Even at this enormous scale, the universe is mostly empty. The total fraction of cosmic volume occupied by the visible matter we have toured tonight, every star, every planet, every nebula, every galaxy, every cluster of galaxies, is unimaginably small. Most of the universe is soft, empty space, with the matter clustered very gently along the soft strands of the web. The universe is roomy, not crowded. The universe is large enough to hold all of its slowly turning galaxies and still have enormous quiet stretches of nearly nothing in between. Most of the matter binding these structures together is dark matter invisible to light, yet shaping the gravitational scaffolding on which every galaxy hangs. We cannot see the dark matter directly, but we can feel it indirectly through its gravity. We see galaxies turning faster than their visible stars alone would allow. We see clusters of galaxies bound together by more gravity than their visible mass can account for. We see the large-scale pattern of the cosmic web traced not just by visible galaxies but by the long, unseen frame of dark matter that holds it together. Over the deep future, cosmic expansion will slowly carry the most distant filaments out of reach. The wider universe is gently expanding. Distant superclusters that are not gravitationally bound to us will, over billions of years, drift farther and farther away. Our own region of the web, Laniakea, the local group, the Milky Way, will become a quieter, more isolated island. The bound galaxies will stay together. The unbound ones will recede. The night sky of any far future descendant world will eventually contain only the slow, merged remnants of our local family, with the rest of the universe softly out of view. We have stepped, in this room, into the largest pattern the universe shows. The cosmic web is the broadest soft structure we know of. From here, only one more room widens before us, the room of the observable universe as a whole, the soft edge of all the light that has had time to reach us. Step gently with me. The largest seeing waits. Before we step outward into the largest seeing, settle for a moment longer in the cosmic web. The slow, patient web of galaxies has more soft details than a single passage can hold, and a few of them are worth lingering with gently. The filaments of the cosmic web are not empty. Along them, between the bright clusters of galaxies, run long, quiet rivers of hot, thin gas, the intergalactic medium. The temperature of this gas is millions of degrees in many places, hot enough to glow softly in X-rays, but its density is so low that it would not feel like much to any imagined traveler passing through. The intergalactic medium contains more ordinary matter, by mass, than all the stars in all the galaxies put together. Most of the visible matter of the universe does not live in stars or planets at all. It lives in the soft, thin, diffuse gas threaded between the galaxies, drifting gently along the strands of the web. At the soft junctions of the filaments, where many strands meet, the great clusters of galaxies form. Inside a large cluster, the galaxies move quickly, sometimes thousands of kilometers per second, held in soft orbit by the combined gravity of the cluster's many galaxies and its much larger reservoir of dark matter. Inside a cluster, galaxies often pass close to each other, occasionally merging slowly into one larger galaxy. Some clusters contain a single dominant giant elliptical galaxy at their center, formed over billions of years by the slow, patient mergers of many smaller galaxies that drifted to the center over time. Between the largest superclusters and the largest voids, the universe is gently knit together. Look closely at simulations of the cosmic web, the soft computer pictures of how dark matter is thought to be distributed at the largest scales, and you will see what looks like a vast, quiet network of bright, slow strands, gentle dark spaces. The bright strands are where the dark matter, and therefore the galaxies, have settled. The dark spaces are the great soft voids. The patterns are similar across many different scales. Clusters of galaxies inside superclusters, superclusters inside larger soft structures, all of it arranged on the slow, patient web. It is the largest pattern the universe shows. It is also the gentlest. Even at this scale, there is no urgency to anything. The web is simply, slowly, holding itself together. The cosmic web has been growing for billions of years, very gently, as small, slow seeds of denser regions in the very early universe gathered more and more matter under their gravity. The larger structures are still slowly settling, even now. The web is not finished forming. It is a slow, patient sculpture, and the universe is still working on it. We are inside the sculpture, on a small, soft thread, in a small, soft galaxy, on a small, soft star, on a small, soft world, and the slow shaping of the wider web continues all around us, gently, every moment. Step out one more time. The next room is the largest room we will enter tonight. Beyond the superclusters and the cosmic web lies the soft edge of all the light that has had time to reach us. This is the observable universe, a sphere of seeing, gently centered, by accident, on the listener. The observable universe is the portion of the wider universe whose light has had time to travel to us since the cosmos began. It is not the whole universe, almost certainly. The wider universe is much larger than what we can see. But the observable universe is the part of the universe we can, in principle, have information about. Anything outside it has not yet had time to send us any light. Light from the most distant places we can see has been traveling for about 13.5 billion years. Nearly the entire age of the universe. The deepest images of the sky, taken with the largest telescopes, pointed at the darkest patches of space for hundreds of hours at a time, show us galaxies as they were when the universe was just a few 100 million years old. Small, fragile, early galaxies, soft and red and irregular, still in the slow, patient process of becoming the great spirals and ellipticals they would one day be. We are seeing them not as they are now, but as they were almost at the beginning. Their light has been on the road for nearly all of time itself. But here is a quiet, curious fact. In all those billions of years that the light from those distant galaxies has been traveling toward us, the universe itself has been expanding. The points of space that sent us those first photons are now much farther away than the photon's travel time would suggest. Today, the most distant edge of the observable universe sits about 46 billion light-years away from us in every direction. That is the comoving radius of the observable universe, the actual present-day distance to the points of space whose oldest light we are receiving now. So the observable universe is a sphere about 93 billion light-years across, with us at the soft center. 46 billion in every direction. A sphere larger than its own age, in light-years, because the underlying space has been expanding. We are, by accident, at the center of our own observable sphere. But this is not a special place. Every observer everywhere in the universe, sees their own observable sphere centered on themselves. There is no central point of the universe. There are only countless overlapping circles of seeing, every one of them centered on its own quiet observer. A galaxy a billion light-years from us is also at the center of its own observable sphere, and its sphere overlaps with ours, but is not the same as ours. From its vantage, slightly different parts of the universe are reachable by light. From our vantage, slightly different parts are reachable. The universe is gently fair about its largeness. Every observer is, in the only way it can mean, at the center. Within our observable universe, there are, by current best estimates, roughly 2 trillion galaxies. 2,000 billion galaxies. Each one a soft city of stars in its own right. Each one with its own slow turning, its own population of nebulae, its own quiet black hole at its center. 2 trillion galaxies. The number is too large to picture as a count. It is closer to a soft flavor of largeness than to a real quantity. Each of those galaxies contains, on average, somewhere around 100 billion stars. The total number of stars within our seeing is, therefore, roughly 2 trillion times 100 billion. About 200 sextillion. A 2 followed by 23 zeros. More stars than there are grains of sand on every beach on Earth. Many, many more. Each one a sun. Each one slowly burning its quiet fuel. Each one quietly carrying, almost certainly, at least one planet. For every star, there is, on average, at least one planet. Worlds, in the observable universe, outnumber stars. There may be more planets than stars by a factor of 2 or 3 or more. The total number of planets we can in principle see is therefore comparable to, or larger than, the number of stars. Hundreds of sextillions of small, soft, round worlds drifting in slow orbit around their parent suns, scattered through the soft strands of the cosmic web. Each one with its own surface, or its own atmosphere, or its own oceans, or its own snowy plains, or its own quiet desert. We cannot visit them. We may not even, in the lifetime of any one civilization, ever know them by name. But the universe holds them, gently. The faintest, oldest light we can see is not from any galaxy at all. It is from the universe's first transparent moment, a soft glow filling every direction of the sky. This light was once an enormous warm glow of plasma, when the universe was younger and hotter and denser. As the universe cooled and expanded, that glow stretched and reddened and cooled along with it. Today, it has been stretched so far that it is no longer visible light. It is now microwaves, radio waves, with very short wavelengths, only a few millimeters long. We call it the cosmic microwave background. That ancient light fills every direction of the sky, very evenly and very faintly. Its temperature, as a glow, is about 3 degrees above absolute zero, about negative 270 degrees Celsius. A faint hum, only just above the coldest possible temperature, gently bathing the entire universe. You are, at this moment, gently bathed in that light. Most of it passes through you and through everything else without being noticed. A very small fraction of the static an old television produces between channels comes from it. The whispering radio hiss of the universe is, in part, a faint signal from a moment a few 100,000 years after the universe began to be transparent at all. The oldest light we can detect, woven softly into the noise of our own technologies. Beyond the cosmic microwave background, our seeing softens. There is no sharp wall. There is only an older and older universe that becomes harder and harder for light to leave, and finally, a beginning we can model in our equations, but cannot directly view. The universe, before the moment of transparency, is hidden from us by the warm fog of its own younger self. We have other ways to probe it, through the slow, careful study of the cosmic microwave background's small temperature ripples, through the patterns those ripples leave behind in the distribution of galaxies, through the slow, distant whispers of gravitational waves. But direct seeing softens at that edge. The earliest light is the farthest edge of light itself. The observable universe is not the whole universe. It is only the portion whose light has had time to reach us. The wider universe is almost certainly much larger, possibly very much larger, possibly without any edge at all, possibly infinite. There may be parts of the universe whose light will never reach us, no matter how long we wait. Cosmic expansion stretches some distances faster than light can bridge them. There may be entire galaxies, entire superclusters, entire vast cosmic web filaments that lie beyond the soft edge of our observable sphere and will never be reachable by light from us, even given infinite time. We will never know them. We cannot know them. They will continue to exist, calmly, on the other side of a soft horizon we cannot cross. And over the deep future, more and more of the galaxies we can currently see will quietly slip out of view. Cosmic expansion is accelerating very softly. Distant galaxies, not bound gravitationally to us, are drifting outward at slowly increasing speeds. Eventually, their light will redshift beyond detection. They will fade gently from our sky, one by one, over very long timescales. The observable universe will slowly contract, in galaxies, even though it does not contract in size. The sky of any far future descendant world will be, in this way, slowly emptier than ours. A quieter sky ahead. That is not a sadness. It is, in a soft way, the gentle long form of everything we have walked through tonight. The universe is, at the largest scales, slowly settling into stillness. The bound galaxies stay together. The unbound ones fade away. The cosmic microwave background slowly dims. The light slowly stretches. The very far future will be quieter than the present. The present, in its turn, is quieter than the soft, loud past. We have reached the soft edge of all the light we can see. The room can widen no further. Beyond here lies the wider universe, and it is unimaginably larger, but the only way we have to approach it is to acknowledge it softly and then turn home. Step gently with me now. The last room of the night is small. The last room is the body again. After the long, slow walk outward, gently turn the camera around. The ladder of scale runs in both directions. The smallest end of it is just as quiet, just as ancient, and just as full as the largest. To close tonight, we will turn back to the very small and let the walk inward bring us softly home. The smallest meaningful step in physics is the Planck length. It is about 100 billion times smaller than a proton. It is the scale at which gravity and quantum mechanics blur into a single question, and at which the language of size itself begins to soften. No experiment has ever measured anything that small. We can only describe the Planck length in equations gently. It is a horizon at the bottom of the ladder, in much the same way that the observable universe is a horizon at the top. Between the Planck length and the size of an atomic nucleus is about 20 orders of magnitude. 20 zeros. The same number of zeros, roughly, as the leap from the size of a human hand to the size of the entire Milky Way galaxy. Between the size of an atomic nucleus and the size of a human being is also about 20 orders of magnitude. 20 zeros. Between the size of a human being and the soft edge of the observable universe is again about 20 orders of magnitude. 20 zeros, give or take a few. On a logarithmic ruler, one where each step is a multiplication, not a simple addition, humans sit gently near the middle of the universe's ladder of scale. We are about as far below the size of the observable universe as we are above the size of the Planck length. We are about as far above the size of a proton as we are below the size of the Milky Way. In a very quiet way, we are the size of a bookmark, placed roughly halfway through the book of size. It is a soft accident, a pleasant one to hold, that the body, the small ordinary body sitting somewhere now, listening to this video, is roughly the middle rung of all the size the universe contains. It is a quiet coincidence, of course. There is no rule that says observers should sit at the middle of the size ladder. But it is, for whatever reason, where we are. And it makes the ladder gently approachable from both directions. The very small and the very large are about equally far away. Now turn the camera inward. Inside every cell of your body, ribosomes assemble proteins, one amino acid at a time. The ribosome is a few nanometers across, only a few hundred times larger than the atoms it works with. It is one of the smallest molecular machines in the body, and it is at work right now, in every cell of you, slowly and patiently making the proteins that your body needs to repair itself, to grow, to sustain itself, to dream. Inside every atom in your body, the electrons orbit a nucleus that is 100,000 times smaller than the atom itself. The atom is mostly empty space, very quietly arranged. If the atom were the size of a football stadium, the nucleus would be no larger than a small marble drifting somewhere near the middle of the field. The rest is space, held together by gentle electrical forces. Inside the nucleus, the protons and neutrons are themselves bundles of quarks, bound together by forces no one has ever seen with a naked eye. The quarks are smaller still, possibly point-like, certainly smaller than anything we have ever directly measured. They are held together by the soft, slow, patient work of one of the fundamental forces of nature, which gets stronger, not weaker, as the quarks try to drift apart. So the quarks never quite separate. They are bound forever in their soft, small groups of three. Almost all the mass of an atom is in the nucleus. The electrons, by mass, are almost nothing. Each electron is roughly 2,000 times lighter than a proton. And yet, by occupying space, the electrons are almost the whole of an atom's size. The atom you are is mostly empty space, with most of its mass packed into a tiny, dense center and almost all of its volume held quietly by clouds of nearly massless electrons. The body is, in the deep, small way, mostly soft space. Everything in your body, every atom, every breath, every thought, is made of particles that have existed since the universe was very young. The carbon and oxygen and iron and calcium in your body were forged in the slow, patient work of stars that lived and died before the sun was born. Massive stars, over their lifetimes, fused hydrogen and helium into the heavier elements that the universe needed to make rocky planets and rivers and trees and bodies. When those stars finally ran out of fuel and collapsed and exploded as supernovae, they scattered their heavy elements gently across the galaxy. Some of those elements drifted, over hundreds of millions of years, into the soft cloud of gas and dust that would, in time, collapse and form the sun and the planets around it. and some of those elements, in turn, became the rocks and the seas and the soft, slow life of the Earth, and eventually, the body of whoever is listening to this video now. The hydrogen in the water you drank today, however, is even older. Hydrogen does not come from stars. Hydrogen was made in the first few minutes after the Big Bang, when the universe was hot enough and dense enough to fuse a thin, warm soup of protons and neutrons into the lightest atoms. The hydrogen in your water has been there ever since, drifting through space, falling into the soft cloud that would become the Sunday, drifting through the Earth's slow oceans and atmospheres and clouds, quietly waiting, in one form or another, for nearly 14 billion years. The water you drank tonight contains atoms that have been around almost as long as the universe itself. In a very literal way, you are made of the universe at every scale. The smallest particles in you are older than the Sunday. The atoms in you were made in stars and in the first minutes after the Big Bang. The molecules in you carry the slow, patient memory of all the worlds those atoms have passed through. The cells in you are the small, soft factories of life. The body in you is a quiet bookmark placed near the middle of the size ladder. And the awareness in you, the slow, patient attention that has accompanied us through this video, from the hand outward to the observable universe and now back home, is itself, in a soft way, the universe quietly noticing its own size. The ladder begins inside you and ends inside you. The walk outward we have just taken is also a walk inward. The room widens, and the room narrows, and both are the same room. The universe is layered, like nested rooms, and you, very gently, are one of those rooms. You contain the smallest end of the ladder. You are contained by the largest end. You are the soft center of a small, bright sphere of seeing in a vast, quiet universe that has been making rooms for nearly 14 billion years. And so we let the ladder of scale rest where it has always been, running quietly from the small warmth in your palm out to the soft edge of the observable sky and back again. You are held inside every rung of it, and every rung of it is held inside you. Let your shoulders soften. Let your breathing slow. Let the long quiet of the universe settle around you. Sleep well, and good night. Before the very last words tonight, settle for one more soft moment in the quiet middle of the ladder. The body, with its hand and its slow, patient breath, is the bookmark we have been returning to all evening. The body holds the smallest end of the ladder inside it. The body sits at the gentle logarithmic middle of size. And the body, through its slow, patient attention, has reached the largest end of the ladder too, through the soft work of seeing. The universe is vast. The universe is quiet. The universe is mostly empty space. The universe has been making rooms for nearly 14 billion years, and the room you are in now is one of them. The hand at your side, the breath in your chest, the slow, soft pulse in your wrist, all of these are made of the smallest end of the ladder. The night sky above the ceiling, the soft dark beyond the room, the slow-turning galaxy, the further galaxies, the cosmic web, the observable edge, all of these are the larger end of the ladder. And both ends are, in their own quiet way, the same continuous, slow, patient ladder. The universe is one shape, held softly at every scale.